Okay, so let's begin. And okay, the system we are going to be having in mind, just like in the case of kinetic theory of gases, is an ideal gas, but the mechanical description of this ideal gas with, say, a large number of molecules which are modeled as classical particles inside of a rigid container of certain volume, and they are moving around with different velocities, and bouncing in the walls, and and they don't interact with each other. So that's important. So such mechanical system, if you want to describe, let me just emphasize that the number of particles is very large. If we want to describe the dynamical state of this classical mechanical system, we would need to provide all the generalized coordinates and the corresponding momenta of every single particle. So what is that I mean? Imagine you are in the simplest case of a monatomic gas. So in that case, you would only need to supply what's the position of each y of each particle in any given instant of time, and also you need to supply the corresponding velocities or the momenta, if you like. Okay, so the momenta y and the momentum set I for all the particles from 1 to n. And so this means that the amount of information or different data inputs that you need is twice 3, which is the number of dimensions in this case, and n. Okay, so of course we know that the molecules don't need to be monatomic, and when you have diatomic molecules, for instance, or even polyatomic molecules, you have additional degrees of freedom. This is something we learned before. So there could be, say, rotation, so you would get some additional angular coordinates, and there could be some vibration, so you would get some distances that are oscillating harmonically, and so on. And of course the number of conjugate momenta will grow in the same way. So in general, if you have f degrees of freedom, the number of items of data that you need to supply to fully characterize the mechanical microscopic system of this gas is 2fn. Okay, so and you can arrange this information in a vector. Okay, the vector like this with all the coordinates. That's f times n vector of length f times n, and the corresponding equally long vector of momentum gives you all the information about the dynamical state of the system. So when I say dynamical state, this is what I'm going to be calling microstate from now on. So this is microstate. Okay, so graphically, if I wanted to represent the microstate of a system, I could, although it's quite impractical, I could think that somehow I'm able to think about very highly dimensional space with 2fn orthogonal axes, which is not the case I'm drawing here, of course. That's why I'm putting some dots here, so that there's many more orthogonal axes in every direction that I cannot draw. And any point in this hyperspace is going to be given by a certain set of coordinates and a certain set of generalized momentum. So a single point in this space fully characterizes the dynamical state or microstate of the system. And such space or representation is what we're going to call the gamma space. Space or phase space. Okay, so that's the terminology there. Okay, so however, of course, we know, and this is something we discussed when we started this module, that you cannot go to a system and measure what every single individual molecule is doing, or not even close to that. Okay, so at best you can try to have some sort of spatial resolution in your measurements of your system. So you have your system, you have no idea what's going on inside microscopically, and at best you might be able to measure some intensive properties of your system if you break it down into a grid like this, and you measure, say, pressure and temperature in each of these little squares of the grid, cubes in this case. And that way you get a field, okay? So pressure and temperature, you can measure volume, things like that, okay? But there's no way that you are going to get this precise and you're going to be able to ascertain what every single molecule is doing, okay? And also remember that this kind of measurements that we can do macroscopically are not only they have low spatial resolution, but also they have very low temporal resolution, because kind of dynamical time scales of such systems is in the femtosecond scale, and we just can't, or at least we struggle to measure things that change that fast, okay? So, okay, what we can do is this coarse blunt characterization, which is an effective macroscopic characterization of the system, and this is what we call macrostate, okay? So that's the macrostate of the system as opposed to the microstates. So there's actually a large number of microscopic dynamical states of the system which are compatible with macroscopic observation that we make, okay? That just reflects our ignorance about what the system is doing, okay? So at best I can tell you that this is what I could measure in my system, but I have no idea what every molecule is doing. So there's actually very many different arrangements of molecules in different positions, and very many directions of and magnitudes of velocities that I could assign to each of these molecules that would be compatible with this observation that I just did here, okay? So that is to say that there is a large number of microstates which are compatible with a macrostate, and if you could count what that number is, that's what we're going to call capital omega, and this is going to be called the statistical, sorry, I just wanted to change color, statistical weight of a macrostate. Let's write it here, of a macrostate. So it's the number of compatible microstates, okay? So what is plausible that the system is doing microscopically, given that I only have this incomplete information. Now, one important thing to say about this is that the system does not need to be in thermal equilibrium, okay? We know if the system is in thermal equilibrium, rather than having to measure locally the pressure and the temperature, for instance, I could just give a single scalar value for the whole system because it's constant everywhere, okay? So in that case, the system is in equilibrium. I could also infer from measurements, from macroscopic measurements, I could indirectly infer all the other thermodynamic properties that we know, okay? So like internal energy, or enthalpy, or the Gibbs potential, and so on and so forth, free energy, even the entropy or the entropic potential, so you know, all of the things that we have learned in the pure thermodynamics parts of the module, okay? So well, that is to say, just again to emphasize, macrostates, usually we are going to be thinking of equilibrium. They don't have to be of equilibrium. They're just macroscopic blunt measurements with low spatial and temporal resolutions of otherwise microscopic systems with a large number of molecules, okay? And remember this notion of statistical weight, because we are going to be using it a lot. How many different configurations would make sense, would be compatible with this incomplete information I have extracted macroscopically about my system. Okay, so now let's get to business already, and let's introduce Boltzmann's entropy. So Boltzmann entropy. Okay, so or Boltzmann principle, if you like. So the formula is this. Let's just call it SB, and I will explain why in a moment. It is proportional to the logarithm of the statistical weight. So if I have a macroscopic thermodynamic system, and I establish what the macro state of the system is from coarse-grained, blunt, macroscopic measurements of whatever I can measure in my system, well, that will be compatible with some number of microstates. And I somehow calculate them, take the logarithm, and I define an object which is proportional to that logarithm. And this is called statistical entropy or Boltzmann entropy. Statistical, well, let's just call it Boltzmann entropy. I mean, it's just written there. Good. A more insightful way to maybe look at it is something that Planck liked to do, which is exponentiate this. Okay, so let's just exponentiate this equation. and we arrive to something nice. Okay, so imagine for a moment that this entropy, this statistical entropy, can be inferred maybe indirectly, macroscopically, from macroscopic observations. Okay, so if you measure that, which maybe you can infer it macroscopically, you exponentiate it, and you get information about the inaccessible internal microscopic workings of your system. Okay, so this equation is connecting the microscopic world with the macroscopic world, and this is what makes it so beautiful. Okay, it's one of the most beautiful equations of physics, as has been described, and it's in fact engraved in the tombstone of Boltzmann. Okay, so this is what you find in the memorial of Boltzmann. And okay, so one thing to mention is that I am writing SB, and I call it entropy, but I make sure to make a distinction between this thing that I just defined for no reason and what we know is the true thermodynamic entropy from thermal physics. So we don't know whether this thing is equal to that, or under which circumstances they are equivalent or equal. It's just something that just happens to be called entropy for the moment being. So now what I want to do is to give you some arguments that at least such definition. So if I were to define statistical entropy, this definition would be a reasonable one to take. Okay, so let's just give two arguments. Later in this lecture, I'm going to give more reasons to believe that, actually many more reasons, and then we will be quite happy to make the connection between Boltzmann entropy and the true thermodynamic entropy, at least if my system is made of non-interacting particles, for instance, in the case of an ideal gas. In this case, they are equal. Okay, but this is advancing things, so let's just consider first, like a thought experiment, what happens here. So imagine you have, okay, let me copy this, paste it, something bad happened, sorry, there you go. So imagine that you have a system like this. So all that I'm trying to draw is, of course, a rigid container with thermally insulating walls, and you have your gas here. So imagine that the system is in thermal equilibrium. Imagine that you can, at some instant of time, you can take a picture of it. Okay, and you know exactly where every molecule is. So it's a very special type of camera that can do that. And you somehow know also what the velocity of everybody is here. Okay, so you know the microstate. So what happens then? And by the way, and also you make sure that you measure the pressure, say, and the temperature of this system. And it's in equilibrium, it's homogeneous everywhere. Okay, so I just ask you, what happens if I take this molecule here and that molecule there, and I swap them? Do you think that the microstate that I obtain after swapping these two arbitrary molecules in this extremely large number of molecules in the gas, is it going to become somehow incompatible with my macroscopic observation that pressure is given by some value P and temperature is some value T? Well, of course not. Okay, and I could even move them a bit here and there, or I could accelerate them a little bit or make them a little bit slower. Because, I'm just changing a couple of molecules. Who cares? Nothing will happen from the macroscopic perspective. I would need to do something much more disruptive to change the macroscopically observed thermodynamic variables for this system. Okay? So what I'm saying is that just taking this picture, taking this single microstate and making all sorts of changes, small changes to it, I get a large number of additional microstates, all of which are compatible with the same macroscopic observation. Okay, so in a way, if I have a homogeneous system, like this one that I'm drawing, I expect to have an extremely large number of compatible microstates. And so the statistical weight of a homogeneous state like this should be very large, at least much larger than an inhomogeneous configuration like the one that I'm going to draw now. Okay, so imagine that for some reason all the particles decide at the same time to go to this corner here, and there's nothing else anywhere. Okay, so if I were to go to measure pressure and temperature, I would get some singular value here, and then I would get zero everywhere else. Okay, So what microstates are compatible with this surprising observation? Only one. Okay, that everybody is here and nothing is left anywhere else. Okay, and this is extremely inhomogeneous, this state. So if you have an homogeneous situation, well, there's very, very, very many different ways to distribute molecules around that look homogeneous. Okay, you can just swap all possible pairs of molecules and you again have an homogeneous state. But in this case, if you swap particles, you know, the same microstate appears because they are all really sitting onto each other, on top of each other in that corner there. So you don't care if you swap two particles, you get the same microstate. There's only one. Okay. Of course, this is an extreme case, which is just to illustrate that if you choose your statistical entropy to be a monotonically increasing function of the statistical weight, well, that's good because it seems somehow to be compatible with this notion we have that when a system is in equilibrium, that is homogeneous, its entropy is maximized when it's isolated, thermally insulated. Okay, so if we choose something like this, because the logarithm is one example of monotonically increasing function, that looks reasonable. Okay, I'm not saying that that's why we have proven that this is equal to the thermodynamic entropy. Of course, we haven't proven that, but you know, at least that is a reasonable choice. Now, another reason to believe that it's going in the right direction is to go to the additivity of entropy. Okay, so if you remember the chapter of entropy, we said entropy under some assumptions that we discussed at the time of weak interactions and so on. If you have two systems in thermodynamic equilibrium and you combine them together, the entropy of the resulting combined system is the sum of the entropy of the parts. Okay, so fine. Let's just see then that this choice of function, so I will advance you the result, is the only choice possible which is monotonically increasing and it satisfies this additivity property. That is, if you have one system in equilibrium, A, and the corresponding statistical weight of that equilibrium state is omega A, and you have another system which is also in equilibrium, certain macroscopic equilibrium state, and the associated number of microstates compatible is this omega B. When you combine the two systems, the statistical weight of the combination is nothing but the product, of course, of the statistical weights. Okay? For every single configuration of subsystem A, you have to consider all the possible arrangements within system B as different microstates, because they are then. Okay? So this is the final, the combined statistical weight. So what I'm asking is that a good entropy function should be such that this thing, which is actually equal to that thing times that other thing, equals S of omega A plus S of omega B. Okay? So this is what we have to ask that a good entropy function should obey. So let's, and this has to hold for any value of omega A and omega B. Okay, so this is where physics stops, and let's start thinking mathematically. So now we want to find what family of functions is going to obey this, and we're going to conclude that this is the only possible function, plus some constant shift. Okay, so let's replace this thing by x, just notation, okay, some number, real number. And then, well, it should be integer really, but anyway, some number. And then here we are going to replace b because it can be any value. Let's just call it 1 plus epsilon. And in our calculation now, we are going to assume that epsilon is arbitrarily small. Okay, it can be as small as you like. So what we're saying here is that s b, so this sort of entropy function that we don't know what it is, of the product of this guy and that guy, so this thing has to be equal to S. It's raining now. Probably you can hear that. It's been terrible weather this week. So rain or no rain, let's continue doing this. What we want is sorry, this is not what we want. We want that this adds up like that. Okay. So now I'm going to do a Taylor expansion, because I said before that this epsilon is a very small number, so I could make a Taylor series and stop at any given finite order. Okay, so let's just do this in the left hand side. So what you get is s of x. Okay, that's s b of x. That's for epsilon equal to 0, plus epsilon s b prime evaluated at x. Okay, and then there would be plus terms of order epsilon squared, which are very small. Okay, we can actually shove them to the right hand side if we wanted to. And now here I have sb of x, and then I will do the Taylor expansion here. What I have is sv of 1, and then plus sv prime of 1 times epsilon, and like I said before, plus terms of order epsilon squared, but epsilon is arbitrarily small, and I can just throw those terms away. So the first thing we notice is that this guy goes with that guy, fine. And then another thing we notice is that epsilon, I told you, is small, but it's also arbitrary. So in particular, it could be 0. Okay, so what happens is epsilon is 0, that I have sb of 1 equals 0, which means sb of 1 is equal to 0. So I can just throw it away. Okay, and what I'm left with is, sorry, I'm missing something here. What is happening? Oh yeah, I'm missing an x here. Okay, so there is this x that I didn't write. Okay, so what I have, sorry, just a second. This whole rain episode has made me a little bit distracted. Yeah, but that's right. That's what I wanted to do. Okay, so what I'm left with is this times that derivative of my unknown function equals to this thing 1 epsilon. I can call this complicated notation here, because it's a constant, I can call it k if I wanted to, right? So epsilon, of course, goes away with the epsilon, and what I'm left with is that the derivative of sb, I'm just writing it out explicitly, is going to be equal to some constant divided by x, which means that s of b has to be a logarithm, so k times the logarithm of x, plus, if you like, some integration constant c. Okay, but this is the expression that we need to have if we want entropy to be additive. Okay, so that's another very good reason why to consider specifically the logarithm and not any other monotonically increasing function. Okay.